Okay, here we go. What's today? Today is 27th. Okay. We're going to be talking about partial derivatives. I'm going to give you a definition. Definition. The partial derivative of some function of two variables denoted this way. This is the partial derivative with respect to x. I'll put this parenthetically. Partial with respect to x. Or this way. Okay. The partial derivative of f of x denoted f sub x of xy. That's the partial with respect to x. Okay. Or denoted this way, if you have z in terms of x and y. These are the partial derivatives. These are little deltas, okay, lowercase deltas, is equal to the limit as delta x goes to 0 of f of x plus delta x y minus f of x y over delta x. It's very similar to the definition of a derivative in Calc 1. Let me give you the definition of the partial derivative of z with respect to y. That would be the limit as delta y goes to 0, f of x y plus delta y minus f of x y all over delta y. Okay. Those are the partial derivatives. What does that mean, the partial derivative? Well, it means this. If we have some surface, okay, whose equation is z equals a function of x and y, take our paraboloid, for example, z equals x squared plus y squared. And we want to find the partial derivative of this function at a given point. Let's say the given point is 4, 3. It'd be 4, 3, 5, right? Here's a point on the paraboloid, 4, 3, 5. And we want to find the partial derivative with respect to x. What are we finding? Here's what we're finding. If we were to take a plane parallel to the x-axis and intersect our paraboloid, so it included this point, okay? What did I say? 4, 3, 5, okay? This plane would intersect the surface in a parabola. It would not reach the floor and come up this way, okay? So I'm taking my paraboloid, I'm taking a plane parallel to the x-axis and intersecting my paraboloid so it contains this point. Okay? It's going to intersect in a parabola. The slope of the tangent line to that parabola at that point is the partial derivative of this function with respect to x. Okay? Now, if I were to do this instead, take a plane parallel to the y-axis this way, intersect my paraboloid with that plane, it would be a parabola this way. And I would then find the slope of the tangent line of that parabola at that point. That would be the partial derivative of that function with respect to y. So in this direction, partial derivative with respect to x. In this direction, partial derivative with respect to y. Okay? Let's do it. Let's take this and let's find the partial derivatives of z equal x squared plus y squared. And I have a Mathematica thing that will show us this too, the intersection of that paraboloid with these planes when we do the directional derivative. And then I have a directional derivative generalizes this whole process. Directional derivative takes that paraboloid and takes planes not only in that direction, partial with respect to x, and that direction, partial with respect to y, but in any direction. Okay? Take a plane this way. That's a directional derivative. That's the slope of the tangent line in any given direction. We were talking about this yesterday. If you take all these lines that are tangent to the surface at that point, in all directions, we get a tangent plane to the surface, okay? And this directional derivative in that direction will be the maximum, okay? And that's going to be important to us. And the directional derivative in that direction will be like this. And if you go back in the other direction, the slope of that tangent line is negative, okay? Is negative. So we'll do all that. That's what we're doing. But let's use the definition of this partial derivative with respect to x to find the partial derivative of this surface at that point 4, 3, 5. Okay? Everybody with me? Okay, and away. So, partial with respect to x is the limit as delta x goes to 0. F of x plus delta x. Well, let's see. That's x plus delta x squared plus y squared minus the original function, x squared plus y squared, okay, divided by delta x. So we will get the limit as delta x goes to 0, x squared plus 2x delta x plus delta x squared plus y squared minus x squared minus y squared over delta x. That's equal to the limit as delta x goes to 0. X squares cancel. Y squares cancel. What else happens? Delta x's cancel. What's the limit as delta x goes to 0 of 2x plus delta x? 2x, you bet it is. That partial derivative of our function with respect to x is 2x. Okay? The slope of the tangent line. Okay? That tangent line. Here's the point on the paraboloid. Here's a plane parallel to the x-axis. It's going to describe this parabola. The slope of the tangent line at that point, okay, is going to be 2x. And if x is equal to 4, as in the point 4, 3, 5, that slope is 8, okay, in that direction. That's the partial derivative of that function with respect to x. It's 8. Now, as I go in the other direction and hit it with this plane, will the slope of that tangent line be the same as the one in the x direction?
Yeah.
Maybe. The answer is going to be no. Okay, it's going to be different. Okay, it's going to be different because it depends on the parabola that's the intersection. Okay, if it's low enough here, what happens is the slope gets steeper as we get away from the vertex. And if it's up high, well, we'll do it. And then, like I said, I have this in Mathematica. You can see it. All right, 2x, partial with respect to x. This is like Calc 1. What happened in Calc 1 to find derivatives? What you had to do, use the definition of a derivative, okay? And then you use the definition to find some derivatives. And then you use the definition to find some, to prove some properties. And then you use the properties to find derivatives, and you didn't use the definition anymore. Well, it's even easier here. I'm going to use the definition to do the partial with respect to y. We'll do that here. But then, here's the bottom line. To find partial derivatives, what do? You find the derivative of the function holding the other variable constant. It's that simple. So when I have x squared plus y squared, and I want the partial with respect to x, I care about what's happening in the x direction only. Y is a constant. If I'm going to take this plane in this direction, the y doesn't change. It stays a constant. So I can take that derivative of x squared plus y squared with respect to x, holding y constant. And if y is a constant, its derivative is 0, hence 2x is our answer. Go ahead.
Wouldn't it only be different from a regular derivative if delta x wasn't going to 0, though? I mean, I don't know. It's just, it just doesn't.
But you don't like it?
There's something weird off about it. I don't know.
Well, now we have a third variable, so it's a little bit.
Wait, what is
Yeah,
it?
I guess.
What is it?
I'm not really sure.
Okay, but just something you don't like about it.
I get it, but I don't.
Well, what we're doing is You know, it's like in Calc 1 though. If you want the slope of the tangent line in that direction,
Yep.
what would you do? Well, you got this parabola, that's the intersection. Here's our point. We're concerned only about in that direction. Well, what's an approximation? Well, take another point on that, okay? Delta x away, okay? And then what? Well, let the delta x go to 0. That brings this point closer to this point.
Mm-hmm.
The slopes of those secant lines becomes the slope of the tangent line, which is what we're looking for. And we don't care what happens in the y direction. We don't care about that at all. So it's only the x that's
So
changing
we're
here.
like trying to find a plane in the, but just in the x, or
The plane that we're using is parallel to the x-axis. It's only in the x direction.
Ah.
Every y coordinate on that plane is the same.
right?
It's 3 in that point, 4, 3, 5. Every y coordinate on this plane right here is the same 3. It stays a constant. It's only the x that's changing, not the y. And then when I do it in this direction, it's just the opposite. It's the y's that are changing and not the x. That's what it is. Let's do the partial with respect to y. Oh, Teddy doesn't
What
like
if you
it though.
found a flat plane though? Then what would?
All planes are flat. What do you mean?
No, but like on x and y, but not on z. Then what? How would that change things?
Okay, wait. Where's your plane?
Just on x and y.
Oh, like this plane.
Yeah.
Instead of this plane and
Right.
this plane, you want to take this plane and take that, that'll be that circle here, and find the slope of the tangent line, but,
No
well,
slope, I guess.
well, that one would be 0, that's true, because in every one you take, it's,
Well, that one you're just holding z constant.
yeah, you're holding z constant. You could have x squared plus y squared minus z equals 0, but you have to decide what your variable is and what your function is. And now you're getting into
I'm
problems.
just trying to stall so Brandon doesn't fall behind. You
Oh,
can continue.
what a good guy. What a guy, look at that. Oh, man.
That like you're taking a normal derivative. But
Say that again?
if z's constant, you just treat that like a normal derivative.
Yeah, that's
Or
true.
what
If
we
z is a
carry
constant,
on to.
that's exactly right. If z is held constant, you get x squared plus y squared equals k, say. And now what? Now you're going to find just
square
like
one.
dy dx by implicit differentiation.
Yeah.
Nick made it that. Wow. Oh, wait, Nick. And look at Nick. I'm actually recording. So there you go.
Be proud, man.
He's very impressed.
Yeah.
All right. So yeah, if the z is constant, you've got x's and y's, and you can find dy dx by implicit differentiation or whatever. It's true. All right, what I want to do here, here's the partial of the function with respect to x. I want to use the definition to find the partial with respect to y. But then the rule, like I said, is just hold the other variable constant, and we'll do a more complicated one. All right, but let's do partial with respect to y by using the definition. Okay, you ready? No? Dylan, I gotta do it. So I'll tell you what. Let's. If we do the same function, z equals x squared plus y squared. Okay. Partial of z with respect to y is the limit. Delta y goes to 0. It's equal to f of x, y plus delta y. Let me write out the definition for Nick here. Minus f of x, y all over delta y. That's the definition of a partial derivative of the function with respect to y. It's only y is the only thing allowed to change. Okay? The x is held constant. That's equal to the limit as delta y goes to 0. F of x, y plus delta y, that would be x squared plus y plus delta y squared minus x squared plus y squared all over delta y. That's the limit. Delta y goes to 0. X squared plus y squared plus 2y delta y plus delta y squared minus x squared minus y squared over delta y. That's the limit. Delta y goes to 0. X squares cancel. y squares cancel. Delta y's cancel. And the limit as delta y goes to 0 is 2y. And again, what we have here, the partial derivative of z with respect to y is 2y. What do? You take the derivative of x squared plus y squared with respect to y, which means holding x constant. And when you take the derivative of x squared with respect to y, assuming x is a constant, that's 0. And the derivative of y squared is 2y. Okay? So when you take these partial derivatives with respect to one of the variables, the other variable is a constant. Okay? So, here, you guys do one. Why don't you do this? Given z is equal to e to the xy, find partial of z with respect to x, with respect to x. Because if you do it with respect to y, it's the same thing. You got perfect symmetry here. Just swap the variables. Okay, go ahead. You guys do it. I'm going to see if you guys are with me here.
I hope so.
I hope so, too. And then it's going to be like Calc 1, where after you find those first derivatives, then you find second derivatives. Well, we can find second partial derivatives. And then you get mixed partial derivatives, first with respect to x, then with respect to y. And then it gets a little complicated, but not a big deal. Nothing you guys can't handle, that's for sure.
Could you go back a page just for a second?
Back a page, yes, I could.
All right, I'm good.
Okay. Okay. Oh, you guys used the definition, or are you using the shortcut rule?
I was going to use the definition.
Are you going to use the definition? Is that what people are doing?
Between this and the last thing we did, except for with different variables.
This is a function of x and y. I want you to find the partial with respect to x. But I think the way to go here is we don't really need the definition anymore. We did it, and we saw that the definition just said, okay, find the derivative, keep one variable constant, and the other variable is what we're going to take the derivative of. Okay? We can do it both ways, I think. I'm not sure what happens to the definition here. It's probably not nice. You definitely want to use the little shortcut thing that I just gave you. The fact, here, let's do it. What's the partial of z with respect to x? You're going to take the derivative of this function with respect to x, holding y constant. So, what form is this? E to the u. The derivative is e to the u. Du dx. What's the derivative of xy with respect to x holding y constant? It's y. That is correct. I know, that's what everybody messes up on. But what's the derivative of 7x with respect to x? It's not the x, it's the 7. Okay? It's the same thing here. Derivative of xy with respect to x is the y.
That's all.
So it's just y and ex.
Say that again?
So it's just y.
Just y.
But then
Yeah.
there's actually
Y e to the xy.
Yes. No. E to the xy times y.
Y.
Well, y.
I just.
Are you with me or are you playing
No,
with
I'm
me?
with you.
Oh, you are? All right.
I got you.
Everybody okay with this?
I got it.
What can I use this for?
Oh, actually, we're going to use this for solving max-min problems.
In critical points.
The critical values, yeah, we are. We're going to use this in critical values. There's a second partial derivative test for finding out whether maximums, where critical points are maximums or minimums. I'll tell you what problem we're going to solve with this. We're going to solve this problem, this max-min problem. You ready for this? We're going to get some space on the space station. Okay? The space that we're going to get is determined by the corner of the room and a plane that comes slanting down this way. And what we want to do is put in this space the rectangular solid of maximum volume. okay? We're renting that space, it costs a great deal of money, because what we want to do is investigate mating habits of lobsters in outer space under oh, you already know this?
All right, the Russians or the Americans?
What's that?
Russian side or American side of the space station?
Oh,
So are you working with meters or feet?
oh, really? We still working in feet? No, we can't be, are we?
You're trying to switch it over, but it's not working.
Serious? No, are you serious? Because I know we had a Mars Explorer thing crash in the surface because one set of engineers was using feet and the other set of engineers were using meters.
Thank you, Bo.
We should be using meters, but they don't, they haven't like switched over to it yet.
Is that, I'm surprised at that. I'm surprised. But anyhow, let's say we're doing the American side with feet, okay? We want to inscribe in that space the rectangular solid of maximum volume. To solve that problem, we are going to need partial derivatives to test the critical values, to see if they're maximums or minimums. That's what we're going to do. That's one problem we're going to do. There's a lot of them. I'll tell you a cool problem we're going to do. Here's the problem. We can do this. I'm not going to do much more here today. Here's the problem. Find three numbers that sum up to 100, non-negative numbers, okay, that add up to 100, such that the product of the first with the square of the second times the square of the third is a maximum. Three numbers that add up to 100, so that the product of the first with the square of the second and the square of the third is a maximum. That problem is going to be solved by using partial derivatives. First, square the second, square the third, and we want to maximize the product. Any ideas? Any thoughts as to what numbers will work here to maximize that product? What's that? I know.
So it's
A, B squared, C squared.
Okay, so
And A plus B plus C is adds up to 100.
Okay.
That's the problem. Maybe a better problem is this.
Wait, is it a squared plus b squared?
No,
So it's
we want to
A
maximize A, B squared, C squared, that product.
Oh.
Where A plus B plus C is equal to 100.
Oh. Oh.
Are they all different numbers?
No, there's nothing to distinguish B and C, so those would be the same.
33, 33.
No, but you're not far away. You know what a better problem is, if you're going to do it in your head like that, is to do this. The sum of three numbers is still 100,
Right, and then that's
but the product of the first with the second times the 8th power of the third is a maximum. What do you think in that case? A, B, C to the 8th is a maximum, where A plus B plus C is equal to 100. Any clue as to what you would do?
Maximize C.
Obviously, you got to maximize C. Now, would the answer be something like 0.1, 0.1, and then 99.8? Because you're going to take the 8th power of C. That's a pretty big difference there. You're going to really maximize. What's that? It's A, B. You're going to maximize this.
0.98 at the end. 98. Except 1.98.
and that's like the only limitation, right?
Well, the sum has to equal 100.
And that's it.
So what were you saying about that last? How come we can't do the 99.1?
It doesn't work. That's not the answer. But you would think so, because you want to maximize C in that product. You want C to be as big as possible. You would think that you want C to be like 99, the others be like half and a half, or 1, 1, 98. There's nothing to distinguish A and B, so A and B are going to be the same. Okay? They're going to be the same. But that doesn't work. It doesn't work to have 1, 1, 98. What does work is a little bit closer together, not a heck of a lot. Obviously, C is going to be bigger than A or B. What's that?
1/3, 2/3.
Not that close.
There's already solved.
Use the logarithm.
It's a maximum problem we're going to solve with partial derivatives. We're going to need partial derivative. The answer is
Oh,
10, 10, 80. Maximizes that product. 10, 10, 80. And it's really kind of cool that those problems all have the same solution. The ratio of the solution, 10, 10, 80, 1, 1, 8, is exactly the ratio of the exponents, 1, 1, 8. So if I ask you this problem, maximize the product of this one, let's say a b cubed c to the 6th power.
136.
Yeah, that'd be in a ratio of 136. It'd be 10, 30, 60. That would maximize that product. And it's kind of cool the way that works out.
When you do
the-
have that decimal,
Bless you.
decimal 100, right?
What's that?
That only works unless you have the 8.
Well, yeah, because of the 100, but it doesn't matter what the sum is. The ratio has to be 136. It just turns out if they're in a ratio of 136 and they add up to 100, it's going to be 1038, 60.
Only when they're multiplied, you start summing things together.
Yeah, it's
So
kind of
the
cool.
the a plus b squared plus c squared would be 40 or 20, 40, 40.
If you want to do a squared, which one did? Oh, the one I did in the beginning.
A times b squared.
Times c squared
Yeah.
would be 20, 40, 40. Yeah, exactly right. You're right. That would maximize that product. No other way of dividing up that 100 into A, B, and C will give you a product as great as that one. That's the greatest one. All right, well, that's partial derivative. We just started in. What we're going to do tomorrow, we'll continue with partial derivative, we'll do second partial derivatives, mixed partial derivatives. And we're going to be using these for various things along the way. This chapter is going to take us a while to get through. Obviously, if I do it like I did today, it's going to take us forever to get through it, but we will eventually get through it. Okay? I'm concerned all these people aren't here because they're...
So, Burns, I'm still kind of confused on
You're gonna do the
Oh,
same.
how that's a maximization of the problem there, for a plus b plus equal 100. Are you saying like the numbers will solve like 1, 2, and 2 if it was a, b squared, c squared?
All right, say that again. Now. Which one are you looking at? This one?
Yeah, let's say that one, a, b, c to the 8.
A, B, C, D, 8. This is a 1, that's a 1, that's an 8.
Right.
You have to have your numbers in that ratio of 1, 1, 8. So the way to solve it is say, okay,
We
there.
haven't
So
solved
we
them
have
yet.
15.
What's that?
We haven't solved them yet.
No.
Okay, we only know that those are the exponents.
Yeah,
Okay.
yeah.
We live 50 minutes.
That's what I was looking
Like
for.
that.
Are you saying that c is 8?
All right, wait a second. I have to do,